So today we are pleased to welcome Professor Giovanni Rallo from the University of Pisa. Professor Rallo works in the field of agrohydrology with a strong focus on sensing, modeling, and irrigation decision support in sustainable agricultural system. So it's a pleasure to have him with us today. So Professor Giovanni, the floor is yours. Go ahead, please.
Okay, in my presentation, I will show some experience about my laboratory on agricultural sensing and modeling to irrigation scheduling in complicated and very complex agricultural systems. Just some news about myself. I'm work at the Department of Agriculture and Food Environment at the University of Pisa. My background is in agricultural hydraulic and hydrology, and I skills in food mechanics, hydrology for the soil, the plant, until to investigate complex processes, phenomena like droughts. I leave here some information about some database where you can find some details about my scientific career. Okay, I said I lead that in the University of Pisa 10 years ago. I opening this laboratory specialized in agricultural sensing and modeling, and this laboratory integrated three missions of the university, in particular technology transmission. We deliver several courses about water resource management that's moved from physical application like agriculture, hydraulic, and hydrology until to laboratory with hands-on activity for students regarding the implementation of a decision support system for irrigation scheduling, but also for droughts monitoring. We transfer technologies on the field to the farmer. Usually we transfer technology regarding wide sensor network for irrigation scheduling, but also for drought analysis and audit. And at the same time, we create technology with different patents regarding instruments to monitor the crop water status, to detect crop water state function, and so on. I will show you something, but a lot of detail you can find inside the website. About this relation, I try to show my main activity in technology transfer, in particular the main issue that I experienced during my career in research and in technology transfer missions. So the first part, I would like to explain from my side the complex of our system, physical systems, then to introduce the smart irrigation, the main rule of the zoning analysis and the delineation of a managed zone area. So we can move to talk about feedback control irrigation scheduling with wide sensor network, with soil and or plant or soil and plant sensor, and feed forward the control irrigation system for to schedule irrigation with modeling, in particular energy mass balance approach. And inside this, I would like to extend our discussion about the importance of water stress function, crop coefficients, and the possibility to integrate smart materials in order to reduce the mathematical algorithm of our model. You will see. Okay, about the drought phenomena, we know that all born from the anomaly that we are experiencing in the last century. We recognize also in Italy an increase of about 1.5 degrees of temperature, with an impact on the territory very very important. For example, about the industry clean for the vineyard management, we see that this summer increase. So that means that we need cultivar or variety with different behavior respect the natural one. What happens with this anomaly? Sure, increase the we increase the atmosphere demand, so the crop water consumed according to mathematical analogy Penna-Montate, so with an atmometer that we can use to measure it. And at the same time, we observe an increase of the frequency for flash drought phenomenon. That's very dangerous for us because when happens, usually every 4 years, we experience a flash drought phenomenon which are completely born of the vegetation. So it's difficult to face. About the system, our system is delineated with the irrigation scheme. We are inside an irrigation scheme served by a public resource, usually a dam or a lake or a big river, that releases water according to irrigation collective conveyance system at the sector or district target. Inside its district are nested the farm, served with a second order irrigation distribution water conveyance network. That's our system, and we include also the natural ecosystem because we know that we collect water from a natural resource or stop a river, we change the ecological service of the downside territory. So we need the governance impose us to maintain a natural ecosystem, so to maintain a minimal water flow to recharge, for example, some wetted area and so on. At this level, for us, the efficiency that will be our indicator to characterize our target, that at this step will be the irrigation scheme, is the ratio with a beneficial use of the water, so the summary of the water amount delivered inside each district, with an addition about the amount of water delivered for the maintenance of what natural ecosystem, divided the amount of water uptaken from the riverside. This is a conveyance, a SUSTAGRI water use efficiency that summarize all the gain or loss of the system. The complexity of the system, we know that is physical, and we have also a complexity about the interaction among the different actor of the system. Is very fragmented in space. We move from irrigation scheme, but we go in a very little space, like from the single tree in time, because our crop change during the time, and also we have a multifunctional, multi-user presence. So that means that when we increase, for example, the water use efficiency at this level, the gain is not sure, because, for example, when we pass for an irrigation conveyance network from a natural channel to a impervious channel, or better, to a pressurized network, is sure that will increase the irrigation, the water use efficiency at scheme level, because we reduce the deep percolation, we reduce evaporation, but it's sure that we reduce the groundwater recharge. Groundwater recharge is used Okay, is used in the downside. The groundwater will be used in the downside in other territory for to maintain the well water table or to maintain a wet the area. And so, in some cases, in some countries, we observe that an increase of water use efficiency at local target doesn't mean an increasing in all territory. In some parts, especially in the downside of the system, we observe a lost ecosystem service. I said we can analyze the water efficiency according to the spatial targets. For example, we can move inside the farm, we can move inside the field, nested inside each farm, and inside each field we can delimitate the hydro zone, and so we can expose the hydraulic chain of the water use efficiency. At the same time, with sensor or model, we can move in the hydrological chain by quantifying the efficiency, what is efficiency at plant level, according to the relation with the transpirated volume respect the amount of water delivered in the root zone, and also with respect with the soil. In this case, we use the reciprocals, the reciprocal terms of the inefficiency in the evaporation. And in this case, we observe that the water use efficiency will be the product of among each water use efficiency from the farm to the soil. This is the next approach is used to approve where there is a limit in efficiency that affect the full water use efficiency. Then we know that this transpiration needs to produce production yield. So there is a strong nexus with the water productivity chain, because with transpirated volume allows the plant to photosynthesize and so to product biomass, and from biomass to product yield. In this chain, we know that the hydrology and the hydrological skills is not necessary, because the background is especially agronomic, by selecting the best species of cultivar with the best harvest index, with a good training system, and so on. I don't know how can delete this. Okay. So. After we delineate the geometric aspect of our system, that we see is very fragmented, it's moved from irrigation scheme to the plant, towards the plant level, and then we need to characterize the system in terms of physics behavior or physical function states. For example, we need to know the water stress function, how the crop responds to the soil water status, and also we can totalize of the effect inside another status function, like the crop water response function, where in this case, at the irrigation depths that we deliver correspond a relative yield behavior. This is to function allows to quantify, okay, the water stress level that our system reach, and at the same time quantify the response in terms of yield. What is this function? We study a lot in my laboratory this state function, because allows to select the new climate ready crop according to according to the shape and parameter of the water stress of the function, the mathematical function. We know that critical water status is a feature, a traits for the crop. For example, a crop with the higher soil water status, so closer to a feed capacity, face the stress with difficult to respect the other one, xerophytic plant, that's where the critical water status is closer to the minimal functional water status. We have different shape. Each shape characterize the behavior of a plant. For example, convex shape is characterize the xerophytic plant. The concave shape instead is specific for very sensitive plant. Linear shape regards the medium plants. We studied this function in an hydropower screening system. It's a modular system where we measure with high frequency the soil water status, plant water status, atmosphere condition, and so on, in order to obtain a very detailed screening about the crop water response, or also yield, biomass response, respect the droughts. We can discriminate the effect of the atmosphere, and the end we obtain the water state function and the relative parameter that we use to characterize a different genotype studied in this system. Okay, this is an overview of the system. It's all automatized. We lost a lot of our time to design the best soil moisture sensor, and we moving to a pod that integrate a TDR probe. In this case, we avoid a very important problem regarding the non-representative soil water status measurement, especially when we have a high gradients of soil moisture due to the micro-irrigation, so localized application of water, but also due to the gradient in the water uptake process, especially when we have a root zone very sparse, very sparse. Also, we control the quality of the trial by studying the effect of the filling process with the soil, the plots, and in some case, when our colleague send us the material to be proved, we observe a strong effect of soil bulk density due to the different soil volume used to filling the pots, in root weight density, so in the root growth, also in the amount of biomass of the crop. So that's important to characterize in order to increase the accuracy. Regarding smart irrigation at farm level, the farm is our partial targets, and our object is to move back the maximum of relative yield over the crop response with the minimum using a minimum value of irrigation depths, quantified according to sensor or model. This is very important, especially in some crop like vineyards, where we can in this case also impact with a sustainable stress, and so that's allow us to maintain or in some cases to enhance the quality of the production. In smart irrigation, I'm to respond to 4 questions. For example, how to irrigate, so select the best irrigation plan with the best hydraulic material with a pressure control, high pump efficiency, and so on. This is the apex of my shows. Then, when we design the best irrigation plan, we can select the best sensor or model sensor instrument to quantify how much water we have to supply, when supply this water, so when irrigates, according to feedback control or feed forward control irrigation scheduling. And at the same time, if we have awareness, about the spatial variability of some functional variables or some proxy, we also can recognize where apply this water and with which intensity. Regarding the irrigation plan, we know that if irrigation plan is not good, so with a low efficiency uniformity due, for example, for a low quality of irrigation material or a topology of the meter not appropriate, or with some problem in the design, we can reduce the Keller-Carmelli efficiency uniformity index, and we see that also we quantify with high accuracy the irrigation volume will be impossible to reach the maximum one. So the irrigation plan, the design irrigation plan quality is mandatory in a smart irrigation, in the smart irrigation paradigm. Another important thing that we studied, we face is regard the variable rate irrigation. Variable rate irrigation is not possible for all kind of irrigation distribution systems. It depends sure from the wetted area. And in some cases, like micro irrigation, we can wet an area of very, very little with 1 square meter, for example. But in this case, we can apply the variable rate irrigation because we can't control the single water discharge of a single emitter. So the unique system suitable for variable rate irrigation will be the irrigation system with the mechanic part, where I can control the water flow according to a mechanical variables, easy to control. Why is important is I think it is important because allow us to select the best method or the optimum method for the monitoring of the water status and so on the water stress. We know that we have a system that measure the amount of water, for example, at the leaf level. At the same time, we can move with a large scale with, for example, satellite products, where the water status regards a pixel, for example, 100 square meter. So the level of detail, I think, will depends a lot from the level of application of your irrigation system. So if we irrigate at micro irrigation, for example, with micro irrigation, is sure that we can wet the 1 square meter, but we know that when we irrigate, we going on a set of emitters, so the wetted area will increase. That means that it is not suggested to use diagnostic instruments with high awareness. So we can move towards system with a lower awareness, like satellite products. I see that in the bibliography, someone, so they are founders of research, is trying to product this kind of emitter where we can control for example, the hydraulic section, and so control the water flow according to request of the zone where irrigates, but is in the frontiers. About where irrigates, we know that to delineate the homogeneous zone, we can use proxy variables. The best one could be the water function, the water productivity function or its parameters. So partialize this, but it's impossible because we need a longer time. So we use usually we use proxy variables like yield, plant vigor, so physical property. Regarding this proxy, for example, we have this experience in a vineyard to transfer irrigation decision support system. In the first part, we try to delineate homogeneous zone according to NDVI index, and we obtain this pattern. But what we find is that in this case, the effect of the minor vigor in this case is not due to water limiting, but it's due to a problem in iron in the soil, at the time in water, in available water for the plant, because the skeleton is high in this zone. So that means that some wine, the only use of NDVI is not enough to delineate the managed zone. Here we have another experience. We have in our orchard, pear orchards in Arezzo and Tuscany. We to transfer our irrigation resource system before we arrange a minor zone analysis by a fuzzy analysis according to NDVI, electrical conductivity of the soil, flow rate measurements, and elevation. So that's the material that we use to begin, the instruments, and we see that there is a strong effect of soil conductivity. So the higher is soil conductivity, because it's a proxy of plant available water, that means that this greener area stay in a soil with an high plant water in the soil, available plant water. But is it true that if we look at the emitter flow distribution, is it true also that in this side where is high the vigor is also higher the water flow? Because the irrigation plan is not uniform to supply water on the space homogeneously. And this side, for example, the east side receive 1 liter per hour plus respect the east side. So that means that the managed zone will change according to the number of variables that we put inside. For example, if we put NDVI or electrical conductivity of the soil, doesn't change the managed zone analysis. The best combination is free zones. But when you include another factor of variability, like the water flow emitter, we see that the managed zone analysis will be more complex and admit 4 or 5 managed zones. So that means that the best solution include a managed zone analysis with all variables detected, and in this case we suggest to the farmer to split in 3 parts the irrigation plant. So we at this point we transfer the wide sensor network that use Sentech sensors and the Irrimax Live platform, We calibrate the FDR sensors for the two zone of my system with low and high and DY, and we see that there is no difference, not a difference, because the soil was homogeneous according text to part. And we select the upper and lower thresholds. Lower threshold was detected by tentative, in this case, with a validation that's used pressure chamber measurements. We transfer this system, and we see that the farmer maintain the soil water content with very fine behavior inside the optimal range for 2 years and for the tree sector. What happens with this experience? We observe a very enhanced in water use efficiency. For example, the duration of watering ordinary, so before to transfer the technology system, usually the farmer irrigates with 6 or 7 hours for irrigation. With our system, according to a feedback irrigation scheduling approach, we reduce at 2-3 hours for irrigation, and we obtain a strong water saving from 22% to 56% in some plots. Just to close, another experience regards another scheme of the Tuscany in Lucca, and here it's more complicated. Our system, we construct also the PC board that collect different sensors, so moisture, canopy temperature, eye temperature, atmometer, hydraulic variables, and so on. For example, here we detect also the water level of the public channel where the farmer take water in order to quantify the water use efficiency at district level. Okay, then we design and construct the irrigation plan with electric valve that we control remotely. We build a machine learning algorithm to detect automatically the upper lower thresholds, and then we validate especially the lower threshold according to the measured water stress function that uses afflux. Okay, we have also a dashboard and a GUI where the farmer can observe and monitor the crop water status according to the crop water stress index based on thermal temperature, on the soil moisture, and maintain inside the optimal range. I move on the conclusion because past half hour. Okay, I think that we have to remark in this way that we need awareness of crop water deficit use. So we need the sensor or models to quantify the crop water consume, the use, and the crop water status. It's important also the automatization of the irrigation system, and this must be with high distribution uniformity. And also what's important are the farmer skill in expert irrigation management. If we cover this, we observe a water energy saving at the territorial level, depend from the spatial targets, and also we can optimize the human resource. In this way, we can scale our cyber structure. At the same time, if we increase the use of surface water with water harvesting infrastructure and so on, we integrate non-conventional water, we adopt conservative agronomic practice, and we choose climate-ready crop. That means that we have a less pressure on collective and groundwater resource. So in this way, we can have a multi-scale sustainability and resilience of the territory. Okay,